student in the theory group at UC Berkeley, where he is advised by Sanjam Garg. His research focuses on various aspects of cryptography, including quantum and post-quantum crypto. I should announce something before the talk begins. These events are being recorded and will be live streamed on the iQuest YouTube channel. For bandwidth purposes, we would like to request you to keep your microphone and video off until the end. Should you have any questions during the presentation, I will watch the chat box and will interrupt the presenter at the appropriate time. Otherwise, please feel free to ask your questions at the end of the speaker's presentation. Thank you so much. James, maybe you can go ahead and share. Great, thanks.
Yeah, looks good.
Yes.
Okay, cool.
Great.
Yeah, so thanks for the introduction, and thanks everybody for having me speak here. Like Dakshita said, I'm a graduate student at Berkeley right now, advised by Sanjam Garg, and today I'm here to talk about this topic that's at the intersection of quantum information or quantum computing and cryptography. Okay, so this will be about how quantum information can be useful for achieving this cryptographic task of secure computation. Okay, and yeah, like I'm happy to answer questions at any point in the talk. So please feel free to message questions, and Dakshita, you can definitely interrupt at any point to ask questions. So, okay, yeah. So today I'll be starting with some background in classical cryptography. So discussing some overarching goals of cryptography, and then I'll have to basically give you basically describe about this notion of a cryptographic assumption. Okay, so I'll start with some classical crypto background, then I'll touch a little bit on how quantum has been useful in the past for cryptography. So I'll mention a little bit about this notion of quantum key distribution. Okay, and then the meat of the talk will be in part 3, where I start to talk about how quantum information can be useful for this task of secure computation. And I'll go over some of these first works that kind of identified this usefulness, and then touch a little bit on what kind of recent work is going on in this area. Okay. Yeah, so first about just some background in classical cryptography. One task that classical cryptography has been trying to solve for many, many years is this, the main goal of secure secure communication given a shared key, right? So we just have two parties. They each share some prior key, secret key that they somehow agreed on beforehand, and they basically just want to communicate. So this first party, say the sender, wants to send a message to the receiver. And they want to do so in a private or a secure way, right? And so what does security mean? Generally, it means that if we consider an adversary or a third-party eavesdropper, okay, that's looking at this communication back and forth, right? So we assume that this eavesdropper is going to be able to look at this communication line and see what information is being passed back and forth. For security, we want to say basically that this adversary has no idea what's going on. In particular, they don't learn anything about the message that the sender is trying to send to the receiver. Okay, and so this is just the goal of basically achieving protocols for secure communication like this is extremely old. It's been, people have been trying to do this for hundreds of years or even thousands of years, going back to various ciphers and so on. And these days, I guess at least when this communication is kind of non-interactive, like a single message, this is called private key encryption, and it's used everywhere on the internet. Okay. So this is a really basic foundational goal of cryptography. A kind of a little bit of a stronger goal that is to basically achieve this same task, but without having a shared key beforehand. So what if these parties started without any shared information, and they still want to privately communicate one message from one to the other, right? And it wasn't until the 70s that people first realized that this might be possible. In particular, Diffie and Hellman wrote a paper proposing a protocol for this, and actually a lot of these ideas from this original paper are still in use today. Okay, and like nowadays, this task basically is called public key encryption. So basically communicating a message from one party to the other when they don't share a key beforehand. And again, this is also used very ubiquitously on the internet. Okay. So, right. So far I've been talking about these classical goals of secure communication, which cryptography has been focusing on for the past, many years. There's also a stronger task that people now have been studying for about, I guess, 4 decades is what if you want to do something even stronger called secure computation, right? So communication, like I said, is just about transmitting message from point A to point B. Secure computation considers like a bit of a stronger goal where let's say our two parties both have like their own private input now, okay? And basically what they want to do is compute some functionality f over their private inputs. And what this means is that like, this f is just some public description of a function. And after communicating, we want the receiver to learn some information about x and y, in particular f of xy. Okay. So no longer are we just want to like transmit x from like sender to receiver. We actually want to transmit some very specific information about x, like f of xy to the receiver. Okay. And the study of this was, this was first studied around like when modern cryptography was beginning, so in the late 70s, early 80s. In particular, Andrew Yao in 82 gave the first, he was the first one to really formalize what it means for a protocol to be a secure computation protocol and kind of introduce the setting. And one interesting thing about like secure computation as opposed to secure communication is the adversarial model. So in communication, we were basically worried about a third-party eavesdropper just like looking at this transcript of communication and trying to learn something, right? In secure computation, we actually, consider a somewhat stronger adversarial model where we actually allow one of these parties, that's like one of the parties actually participating in the protocol, to be corrupted itself, right? So we could hope for security even when, like, say, this party is adversarial and acting like arbitrarily, maliciously during the protocol execution. And we want to say that, even if this party is adversarial, they're not learning anything about like the other party's input. So in particular, we want to say that this party, like, we want to keep this sender's input private. So what that means is we want to say that this party learns nothing about the sender's input x, except for what it should have learned anyways from the output of the protocol, which is f of xy. And we can also try to guarantee, privacy against like corruption of the other party. If the sender is corrupted, we want to say that they don't learn anything about the receiver's input y. Okay. So again, we're kind of considering a stronger model where actually the parties interacting in the protocol themselves can even be corrupted, and we want privacy against them. Okay. And this, like it's mentioned here, this was first studied in the 80s, and it's been studied very heavily since for the last 4 decades, and it's been like a really kind of foundational notion to the field of modern cryptography as it's evolved over the past few years. And also just to get more of a sense of like why secure computation has been studied so much, I should, give you some like additional motivation for it, right? Maybe to give you a sense of like how useful it is. So, actually, when Andrew Yao introduced the notion, he kind of motivated it with some toy problem, okay, which is now called Yao's millionaire problem, which is basically just like, okay, let's say each of these two parties are, well, he says millionaires. Let's say they want to just like basically compare. They're millionaires and they want to compare who actually has more money. Okay, so basically they want to do so in a way that doesn't reveal to each other actually how much money they have. Okay, so like you can imagine this party, X is their net worth, and this party, Y is their net worth, and they want to communicate and they want to determine like just who has, like, whether X is greater than Y or Y is greater than X. So this f is just like this comparison function. And secure computation allows them to do that, right, without revealing to each other like how much money they actually have. So this is just like a toy problem that was used to motivate this notion. And there's like many more like actual real world applications of secure computation. So for example, auctions, if you want to like submit private bids and then like do some computation over those, this is kind of requires a notion of secure computation. So voting online is a similar story. If you want to submit like, private ballots and then like compute like a private tally over them. Very generally, if you want to, if you have a bunch of like private databases, maybe held by different hospitals that can't share their data, or companies or governments that don't want to share their private data, but yet they want to come together and like compute some aggregate statistics or functions on their private databases. This is exactly what secure computation would be used for. Recently, like privacy preserving machine learning has been a big topic. So like Google basically wants to like, train these massive machine learning models using like all of their users' private data, right? Or all of their users' data, right? But if the users want to keep their data private while still allowing Google to like train these machine learning models, then this is exactly a task for secure computation. Okay. And there's many more, but this is to give a sense of like why secure computation has been so heavily studied over the past few decades. Okay. Right. So this is a discussion of basically the goals of classical cryptography, or three like of the main goals that have been studied in classical cryptography. The next thing I wanted to talk about is this notion of a cryptographic assumption. Okay. And to motivate this, let's go back to the setting of secure communication without a shared key, and recall, let's just think about like what we want out of this protocol, right? So we basically, like for privacy, like I mentioned, we want that an adversary that can view what I'm going to call a transcript. So it can view this transcript of communication, which is all the messages exchanged between these parties. We want that this adversary cannot obtain M, right? And so just what we know so far is that, well, a protocol that satisfies this notion of privacy, on the one hand, this transcript should be efficiently computable from the message M, right? Because these parties need to be efficiently exchanging messages. But on the other hand, for privacy, we want to say that no adversary that views the transcript should be able to compute M. Okay, so this is kind of the security guarantee that I've been describing. Kind of the issue with this, like one issue right away with this, is that like if you think about it, the transcript itself must actually determine what the message M is, right? Like just for correctness, like for this receiving party to be able to output the correct M, it should be the case that this transcript actually determines what M is, right? So this is to say that basically an adversary, if we allow an adversary to run in like arbitrary amounts of time and to basically launch like brute force attacks, just by correctness, they'll always be able to recover this M just by basically trying all possible like inputs, okay, of the parties. Like, so what cryptographers usually do at this point is to say, well, let's hope for like a little bit of a weaker but still a reasonable goal. Okay, so let's try to design protocols that are secure against adversaries that are bounded in some way, which we usually call computationally bounded, which means that like the protocol should be secure against some class of adversaries that run in some bounded amount of time. And usually this bound can still be like, very large, like, thousands of years or something like this, right? But at least like you need some bound on the adversary's computational power, generally in order to argue about the security of such protocols. Okay, so basically we have amended this goal to say that, well, we want to design a protocol where the transcript can be efficiently computed from M, but on the other hand, M should not be efficiently computable from the transcript. Okay. So this situation is what is motivating kind of the definition of what a cryptographic assumption is. Okay, and these are kind of computational problems or assumptions that are at the bottom of like a lot of cryptographic protocols out there today. So an assumption is basically a computational problem, so a description of a problem, some task that can be solved given arbitrary time, right? So it has a solution, but we conjecture this problem to be unsolvable by any efficient algorithms, okay? And we need like the reason that we can't, we need it to be conjectured for the time being, because like this field of complexity theory isn't really to the point where we can actually obtain provable guarantees, like separations between exponential and polynomial time algorithms. So at this point, we need to basically like come up with problems that seem, or that we can conjecture are hard to solve by efficient algorithms. Okay, and this is what the notion of a cryptographic assumption is. And so really the, kind of the canonical cryptographic assumption, maybe the most, well, the mildest one as well, is this notion of a one-way function. So this is a very generic or like general assumption, which is just a description of a function f that is efficient to compute in the forward direction, right? Just efficient to compute. But we assume, or a conjecture is inefficient to invert, right? So basically, if you have some data and you apply your one-way function to it to get some, scrambled output, we want to assume that it's actually hard to compute the data just from that output. Okay, and this is exactly the notion of a one-way function. Okay, and basically at this point, there are like many candidates or many functions, computational problems that cryptographers have conjectured are one-way functions. Okay, and so there's a long list of candidates, like, for example, cryptographic hash functions like the SHA family, block ciphers, and then various problems that come from math or like from number theory, like just multiplication of large primes, modular exponentiation, other problems like noisy linear equations, noisy code words, and so on. Okay, so these all of these like computational functions, or all these functions basically give rise to like candidates of one-way functions, of things that we can assume are one-way. Okay. Right. Yeah. So basically, like I was trying to get across some intuition before when we were talking about the setting of secure communication, that cryptographic assumptions seem to be necessary for achieving this task, right? And indeed, in 89, it was actually shown that the existence of one-way functions is actually necessary for achieving these tasks. Okay, meaning that if you have a secure communication protocol, it actually implies the existence of a one-way function, which of course means that you're going to have to at least assume the existence of a one-way function in order to obtain security or secure communication protocols. And this was shown even for protocols like private key encryption, even protocols where the parties share a key, as long as you actually want to reuse the key across multiple messages. Okay. So let's see. Oh, is there a question that came up?
Yes, there is a question. The question is from Paul. One-time pad is secure, but not a one-way function.
Right. Yeah. So that's actually why. Okay. Yeah. So one-time pad is a way to do, secure communication without any assumptions, right? And that's actually why I have this like reusable qualifier here. So if you want to communicate a number of bits that matches the number of bits of your secret key, you can do this without any assumptions. Okay, using the one-time pad. But if you want to do secure communication with like a reusable secret key, meaning like say you share like 80 bits of secret key, but you want to communicate like many kilobytes of data or whatever, then you need cryptographic assumptions. Then the one-time pad doesn't apply, and you need cryptographic assumptions. Okay. Yeah, hope that answered the question. So yeah, basically, let's revisit like this landscape of assumptions that this landscape of like cryptographic tasks that I touched on before. So we have like basically private key encryption here, public key encryption, and then secure computation in order of increasing difficulty. And what we know is that at least all of them require the existence of one-way functions. Okay, so what about the converse direction? It's actually been known since the 80s that actually, if you want to do private key encryption, then the existence of any one-way function suffices. Okay, so this is kind of a tight result. So to do private key encryption, it requires one-way functions, and like the existence of any one-way function implies it. Okay. So there's also been like many results over the years building protocols for these more difficult tasks of public key encryption and secure computation. But so far, these have all relied on certain like specific or structured cryptographic assumptions. So as opposed to the existence of any one-way function, these rely on like specific assumptions, basically, that have some particular structure that can be used to construct these protocols. And in fact, examples of some of these include like problems from number theory, some of which can even be broken by quantum computers. Okay, so I mean, not all of them, but some of them can even be broken by quantum computers, which is kind of one reason why maybe such structured assumptions are not, are not desirable. So, you could ask like, okay, what about like, can we construct like public encryption or secure computation from the existence of any one-way function? And we're not exactly sure yet, but there was some like negative evidence given by Mpagweza Rudic in '89 that they showed that at least if your like public key encryption scheme uses the one-way function in a black box way, meaning that it only like it doesn't like care about how the one-way function is implemented, then you actually can't obtain such an implication. And so this is some negative evidence, and like even to this day, there are no proposals for how to construct any public key encryption from any one-way function. Okay, so this remains like kind of implication that's not known and seems difficult to obtain. Okay, so this is kind of the landscape of classical crypto with respect to at least these tasks today. Okay, so I think that's all I wanted to say about background in crypto. If there's any other questions, I can take them now.
Feel free to type questions on chat, and James, I'll pass them to you if any appear.
Okay, sounds good. Right. So next, I wanted to talk a little bit about so far everything I've been describing is just purely classical. Like parties are classical machines; they're exchanging classical information and so on. And so in this next part, I want to for the rest of the talk, we're basically going to be asking this question of, okay, so what about quantum information? Can quantum information help us in achieving like these secure communication or secure computation tasks, right? So first of all, why might quantum information even be useful in the first place? I mean, one thing that maybe differentiates quantum information from classical information is that it's like so obviously like physical, right? Like classical information is, you can kind of just, usually you think about it as just like a sequence of like bits or like zeros and ones that can be like, copied and distributed around. And it's more of an abstract thing. Quantum information comes like in quantum particles, right? And so kind of, maybe related to this like notion of physicality is that it's not, quantum information is not necessarily clonable like classical information is, right? We know that there's, no general way to take quantum information and clone it, right? And again, related to that is like this notion of uncertainty. So again, like with classical information, once you obtain a classical bit string, there's absolutely no uncertainty about what that information is, right? Whereas if you obtain some set of quantum information, if you have obtained some set of like quantum particles encoding some information, there still might be uncertainty in basically the classical information you can extract from those particles, right? And these notions of like unclonability / uncertainty can turn out to be pretty useful for cryptographic or privacy applications. Okay, and kind of the first like formalized realization of this was the notion of quantum key exchange or quantum key distribution. Okay, so basically using quantum communication to do this task of secure communication without a shared key. Okay, so recall when I was describing this task, and I was arguing that, well, it really kind of requires computational assumptions because like the adversary can like observe the transcript and try to invert the transcript to learn the message, right? So in particular, if all of this communication back and forth was classical, there's no way to even tell, like there's no way for these parties to tell if there is an adversary on the line observing, right? So there's nothing to prevent an adversary from just like gathering up all of the classical information, taking it home with them, and then trying to, run some algorithm to learn the message. And the parties have no idea if this is happening or not, right? So the key thing that a quantum information allows you to do is, well, let's say that some of this communication is quantum. Let's say the sender is like sending some quantum states to the receiver. And let's say they're encoding information in like kind of a unclonable way. So, what this might imply is that, like, since this information is unclonable, it's like in these physical like qubits that can't be cloned. In order for the adversary to actually be able to extract information from them, or like kind of observe what's going on, they're going to have to mess with these qubits themselves. They can't just like copy them and bring their copies home with them. They're actually going to have to deal with like the qubits themselves that are being transmitted, right? So because of this, the parties, you might be able to set up a situation where the parties can actually detect if the adversary has attempted to observe their communication. Okay, and this is exactly because this communication is physical and quantum. Okay, and indeed, in '84, so Bennett and Brassard, actually show that with quantum communication, because of this property, you actually don't even need any cryptographic assumptions for secure communication, even without a shared key. Kind of in stark contrast to what we know about the classical case. Okay. Right. So this, like, if we recall, like, kind of the landscape of classical crypto, like this changes dramatically when we move to the setting of quantum crypto, which is where we're going to allow our parties to communicate quantumly, like send qubits to each other and run quantum machines and so on. This IL result from '89 completely disappears, right? Because it was based on protocols with classical transcripts. And indeed, you can achieve these two like secure communication tasks without any cryptographic assumptions at all. Like I just mentioned, this BB84 result. And so if you don't need assumptions, we say that these tasks can be achieved information theoretically. Okay. So, I guess the natural next question is, like, if we move on to this stronger cryptographic notion of secure computation, what about this? Like, can this also be achieved information theoretically? Okay, using quantum communication. And actually, somewhat interestingly, it turns out that this is actually not the case. So like Myers and Low and Chow in the late 90s actually showed that even if you have quantum communication, you cannot do like you cannot achieve secure computation information theoretically like you can do with secure communication. Okay, and I'm not really going to explain how exactly they achieve this result, but to give some intuition, or like basically the key difference between the settings of communication and computation is, again, this adversarial model. So with secure communication, you're only worried about, like I mentioned before, you're only worried about these third-party adversarial eavesdroppers, and like the two honest parties communicating can kind of work together to make sure that the eavesdropper is not learning information. But in the setting of secure computation, you're worried about an adversary interacting in the protocol itself. And what these works in '97 basically showed is that there's no way, there's always an attack that an adversary can launch to learn like some information about the private input of the other party, unless you again resort to computational assumptions. Okay. So yeah, this is kind of the landscape now of quantum cryptography. Okay, and this leads to basically my third section of basically, well, given these negative results from Myers and Low Chow, the main question is, well, can quantum information still be useful at all for secure computation? We know that it can't give like truly like information theoretically secure protocols. Can it still be useful? Okay, and so this is kind of the question I want to address in this last part of the talk. Okay. Right, and so yeah, before we get, I do need to introduce like one last piece of background in order to get more into this question. And this is going to be the notion of oblivious transfer. Okay, And what oblivious transfer is it's simply just a very special case of secure computation. Okay, it's a very like simple functionality, right? So oblivious transfer considers the setting of like a sender here that has two messages and a receiver that has a bit B. Okay, and basically the sender would like to obliviously transfer one of these two messages to the receiver depending on the receiver's input bit, right? So the receiver is going to learn one of these like M sub B. Okay, and this is like oblivious transfer is like a functionality, and what it means to achieve oblivious transfer is to come up with a secure computation protocol for achieving this functionality, right? So a protocol where, in particular, the sender doesn't learn anything about the receiver's input bit B, right? And the receiver doesn't learn anything about the sender's like other input M1 minus B that they're not supposed to learn, right? And so this is just like a very simple like special case of secure computation, but like remarkably, again, it was shown in the 80s that actually achieving oblivious transfer basically suffices for achieving secure computation of any functionality f. Okay, and what this means is that like if you can construct a protocol for securely computing oblivious transfer, then there actually exists a protocol for securely computing any functionality f. Okay. Which is pretty remarkable. And I'm not going to really be able to explain like how this implication holds. It's like a different talk. But maybe to get like some intuition, basically like these parties will set up some encoding of the function, like that will first be sent to this receiver, and then basically these parties can use oblivious transfer to like basically obliviously transfer basically one encoded bit of y at a time to this receiver, and then they can like evaluate the encoding on their encoding of y to learn just specifically this output f of xy. So basically oblivious transfer is basically used to like transfer like one bit of one of the parties' inputs at a time, and then everything else can basically be taken care of without any more secure computation. Okay. So anyways, the point of this is to say that, well, if we want to obtain results about secure computation, it suffices to just build oblivious transfer. So our amended question is quantum information, can it be useful for achieving the notion of oblivious transfer? Okay. And to begin to answer this question, it was actually, again, like kind of amazingly, like even back in, 1968, which recall is like kind of well before even like public key encryption or like secure computation are even defined, right? So basically Stephen Wiesner in 1968 had an intuition that the uncertainty principle of quantum mechanics could be used to achieve like interesting communication or privacy tasks, okay? And he like wrote about two of these in this paper called Conjugate Coding. And the first example that he gave is quite literally a description of oblivious transfer, like kind of before oblivious transfer was even defined, okay? And so what he says is, well, you can basically use the uncertainty principle in order to help with this task of transmitting two messages, either but not both of which may be received, which is kind of literally what oblivious transfer does, okay? And his other example actually was the notion of quantum money, so uncloneable currency, and that's a whole nother talk. But what's interesting is like even back in 68, like Stephen Wiesner had an intuition that indeed like quantum information should be useful for tasks of this form. And so indeed the answer is like, yes, quantum information is useful for achieving oblivious transfer. And before I kind of go on and give more information, I'll explain kind of exactly how it's useful. Okay, so I'll give you kind of the end result. So recall that with classical communication, what I had explained before is that, while OT implies secure computation, we have like negative evidence and kind of not really any positive results on constructing oblivious transfer from the existence of any one-way function. Ideally, we want to base it on the existence of one-way function. We don't know how, and we have negative evidence for it. With quantum communication, what quantum communication buys us is exactly this implication, okay? So we know now that the existence of any one-way function implies oblivious transfer, which in turn implies the notion of secure computation and like all of the applications I mentioned before, like secure auctions and voting and computation over private databases and so on. Okay. And so, yeah, this implication is due to like a long line of works studying, basically quantum cryptography and related topics, and was kind of culminated in 2 works this year that actually completed the implication that one-way functions do imply oblivious transfer with quantum communication. So one of these is with me and Doc Shida and a couple collaborators. Okay. So, in other words, what I basically just said is like we have these trade-offs. So if you want to obtain secure computation, you can either use classical communication, like standard classical communication, and then one of like a few structured cryptographic assumptions. Okay. On the other hand, if you're willing to use quantum communication, you can like get away with like in some sense more secure protocols. Well, possibly more secure protocols in the sense that you can base your protocols on the existence of any one-way function as opposed to just one of a few specific structured assumptions. Okay. So that's kind of reiterating what I just said. Before I want to move on, I'm basically going to talk about like how this works a little bit more. But I should say that there are other ways in which people have studied how quantum communication can help with secure computation, and I won't be mentioning those in this talk. Usually these other works study like different like restricted physical models in which you can obtain secure computation, such as the bounded quantum storage model, quantum noisy storage model, and so on. But I will not be mentioning these in this talk. Okay. So back to actually so Wiesner's original idea. So basically his intuition for how quantum information can be useful for this task. So again, we have like a sender with 2 input strings M0, M1. We have a receiver with a bit B. And this is from his paper, okay, this figure. And so this is his like encoding scheme, basically. So basically, he's saying, take the ith bit of M0 and M1, okay? For each bit, just basically like flip a random bit first, and either encode, essentially, if you get 0, encode your ith bit of M0 in the standard basis, or if your bit was 1, encode the ith bit of M1 in the Hadamard basis. Okay, and so this is exactly his proposal. And then, right, what the receiver can do is the following, right? So if their bit B is 0, and basically they want to obtain M0, they can just like, take all of these like say each of these is just like a photon. So you've sent like n photons, where n is the length of these messages. What the receiver can do is just like measure each of these photons one by one, all on the standard basis. And what that means is that, for all of the photons that are encoded in the standard basis, they get some information about M1. For all of the other photons, they kind of just get a random bit completely uncorrelated with M1. Okay, so basically what this means is that they can recover part of M0 and nothing about M1. On the other hand, if they measure each of these photons in the Hadamard basis, they recover part of M1 and like no information about M0. Okay. And kind of the intuition is that like, because they can't simultaneously like obtain information about like encoding in the standard and the Hadamard basis, this is supposed to kind of imply that the receiver can't simultaneously obtain all information about both M0 and M1. Okay. Again, this was an intuition, and it wasn't, there was no like proof of security or anything in this paper. And in fact, it's like not secure if you allow the receiver to kind of like do more global measurements on the entire set of like n qubits transmitted. But this is kind of the basic idea that has shown up again and again in later works. Okay. Oh, yeah, I see another question. Why only part of the information? Oh, yeah. So basically, right. So at least in this proposal, like you're only, some bits are just like bits of M0 encoded in the standard basis. Other bits are just like bits of M1 encoded in the Hadamard basis. Okay. And if you measure, so like basically so if you measure everything in the standard basis, you're only obtaining like, like basically half of the bits of information. So basically like half of M0. And like the other half of M0 isn't even encoded like in this encoding scheme. It's like the sender is like not even sending over half of the bits of M0. They're either sending a bit of M0 or M1. So basically, I think he even like mentioned in the paper, like, oh, you can like try to use like an error correcting code and so on if you want to actually transmit information fully. Okay. Right. So this is the original idea, and this like kind of encoding scheme was formalized a little bit more later. Also in this paper of Bennett and Brassard, they showed how to use this encoding scheme to achieve quantum key distribution. And now these states that were used have come to be known as BB84 states. And these are just like extremely simple, like a set of 4 single qubit states specified by 2 classical bits of information, right? So like you just have like, you either encode a bit in the standard basis or you encode a bit in the Hadamard basis. So what you end up with is 4 possible states, 0, 1, plus, and minus. Okay. And this is like, the extent of like the quantum, this is like as complicated as like the quantum information is actually that you need to obtain secure communication or secure computation. Okay. Okay, so like basically Bennett and Brassard showed how to use like this type of encoding to obtain quantum key distribution. It wasn't until later, so 1988, that Crépeau and Killian gave a proposal for how to use this type of encoding to obtain oblivious transfer. So they actually gave a more concrete proposal and formalization, building on like kind of the work of Wiesner and Bennett and Brassard. Okay, so I can actually describe now basically how this proposal for oblivious transfer works. Okay, so the protocol starts very simply, and also like how key distribution starts. So one party, here the sender, will just sample a bunch of random BB84 states and send them over to the receiver. Okay, just like uniformly random states. And note that they haven't used their input at all yet. They're not encoding, they're not trying to encode their input yet into these states. Okay. So at this point, the receiver just basically obtains like a bunch of qubits, and they have no idea, like, right, by uncertainty, I mean, they just don't know what information is encoded in these yet. So they have to measure them. And what they do is they just sample their own like random set of bases that they're going to measure these qubits in, and like about half of the bases they'll guess correctly, half they'll guess wrong. So for example, this first qubit, they guessed a standard basis, but it was actually encoded in the Hadamard basis, so I'm going to call that red, so they guessed wrong. But like in these 3, 4, and 6 positions, they guessed the correct bases. So what happens is that they measure these qubits in theta prime bases that they guessed. And then what they obtain is like, in the positions where they guessed wrong, just like random bits, kind of uncorrelated with what the sender encoded. In the places where they guessed right, they get actually the bits that the sender sampled, right? So they get about half of the string X. Okay, and after the receiver performs this measurement, then the sender actually goes ahead and sends over like the original bases, that they chose, just to inform the receiver, okay, like here are actually the bases that I encoded these qubits in. And what that allows the receiver to do is know which positions they guessed right and which positions they guessed wrong. So they can now kind of partition the indices into 2 sets, like these 3, 4, 6 sets that they guessed right, and the 1, 2, 5 where they just have no idea about X. So a couple things to note is that so far, like, none of the inputs have been used yet. This is just like a preamble phase, basically, where they're trying to set up some useful correlations. And this is exactly the correlation that they've set up. Okay, so the sender knows, some random string X that they sampled. The receiver knows about half of X. Okay, and they know exactly which bits of X they know and which they don't. And then the sender, from the sender's perspective, they have no idea which bits of X the receiver knows and which they don't. Okay, because they have no idea what these theta primes were that the receiver chose. And so this is kind of emulating something that has been studied in the classical literature called the classical eraser channel, which is where you just send like, basically, you imagine sending like classical information through like a noisy channel that will like kind of erase some bits and leave some bits be, or erase some bits and like basically leave some bits. And the receiver can tell like which bits got erased and which bits got left over. Okay, so basically what's gone on so far is like these parties have used quantum communication to emulate kind of like a classical eraser channel. At this point, the parties can use kind of this imbalance that they have in information to complete the OT protocol, right? So what's going to happen is the receiver, will it has partitioned its like set into these two parts, like one that it knows and one that it doesn't, and it's going to send over like these two partitioned, like the two sets of indices to the sender, okay? But it's going to use its private input B in this step. So it's going to assign IB to be the set that it knows, and it's going to assign I1 minus B to the set that it doesn't know. And of course, the sender still doesn't know which is which, but it just receives these two sets, I0, I1. Okay. And then using those, it can just partition its own string X into these two parts to obtain like Y0 and Y1, right? So, and then, what's going to happen is that the sender will use, Y0 and Y1 are just two different substrings of X, right? And it's going to then use these two substrings, Y0 and Y1, to encode or to encrypt their messages M0 and M1. And so I'm not going to really be specific about what this like encryption scheme really is, but what I mean by this is that the sender is going to encrypt their message M0 using a key Y0, and they're going to encrypt the message M1 using a key Y1 and send over these ciphertexts to the receiver. And this encryption will actually be somewhat like a one-time pad-ish. It's not going to be cryptographic encryption. It'll be more of like a information theoretic encryption. Okay. And so what the receiver can do at this point, well, they know, because they know like these, these bits at the green positions, they exactly know YB, which is just 101. So they can use YB, the key, to decrypt the ciphertext CTB to recover the string MB, right? So this is how, at the end of the day, the receiver actually obtains this message MB. Okay. So this is like the basic idea for the protocol. Now, there's actually an issue with this, and like so far what I've described, there's been no, like I mentioned, there's been no computational assumptions, so there should be an issue, right? Like we know, like I mentioned, there's works that show that actually it's impossible to do oblivious transfer without any computational assumptions. So what's the issue? So let's imagine that we are dealing with a cheating receiver. So there's a very simple attack that they can launch, which is to simply just like not measure their qubits when they receive them. They just like wait and store them and don't measure them, okay? And so if they just like wait for the sender to send over these bases, at this point, they just know how to, like they know exactly how to measure each of these qubits. They measure each of them in the basis theta. And if they do that, they can recover the entire string X, right? And this completely breaks the protocol, right? Because now they just know, if they know the entire string X, they know both Y0, Y1, and they can recover both of M0 and M1. Whereas oblivious transfer is supposed to ensure that they can only obtain one of these two strings. Okay. So basically the issue that we realized is that like, or that we realized here that, well, Crépeau and Killian originally realized in the 80s was that basically a cheating receiver can simply wait until they receive theta in order to measure their qubits, okay? And so we need to fix this somehow, and the solution is to use cryptography, okay? So what we're going to try to do is effectively like force the receiver to measure when they receive these qubits immediately by using cryptography. Okay. And the tool from cryptography that we're going to use to do this is called the bit commitment protocol. Okay. So briefly, what is a bit commitment? It's a protocol between a committer that wants to commit to a bit B and a receiver. And it's basically like the cryptographic implementation of a physical like locked box. Okay. So what a commitment protocol is trying to emulate is a situation where a committer can send over a box that's locked with a bit B inside to the receiver. And we require a notion of hiding, which states that the receiver, like on obtaining this box, cannot learn B. It can't break into the box and learn B. So at this point, everything is hidden from the receiver. But later, we allow the committer to just like send over a key that the receiver can use to open this box and learn B. But on the other hand, we require this notion of binding, which means that once this box has been sent, C can only make the box open to the bit that's inside of it, right? So C cannot change their mind later and like cause the receiver to output like 1 minus B, right? So, we have these like dual notions of hiding and binding. So like hiding is a property that should hold against malicious receivers. Binding is a property that should hold against malicious committers. And, because of this adversarial model, this is actually kind of the thing that Myers and Low and Chow showed in the 90s is impossible without computational assumptions, even with quantum communication, right? So even this like two-party like bit commitment protocol, we cannot construct without computational assumptions, but nonetheless we can try to construct it from weak assumptions. Okay, but anyways, it's exactly this bit commitment protocol that we're going to plug into this Crépeau and Killian's template in order to try to obtain security against malicious receivers. Okay. And so what is the proposal? So the receiver, at this point, we want to force them to measure. So let's say that they measure. What we're going to add is the sender is going to expect the receiver to actually commit to all of their bases that they chose and their measurement results. Okay. So, rather than continuing the protocols before, we're going to first have the receiver send over commitments to all of their like basically the random bases they chose and the measurement results that they obtained. Okay, and what's going to happen is basically that the sender is going to basically challenge the receiver to open some subset of these commitments. Okay, to basically make sure that at least on some of them the receiver is acting honestly or is honestly measuring, right? So here, let's just say they challenge them to open the second and fourth position. The receiver will just send back keys, right, for the second and fourth position. And what's going to happen is that the sender will open them, okay, and look at all of the opened positions where the receiver guessed the correct basis. So in this case, this fourth position, the receiver guessed the correct basis, right, the standard basis. And so if the receiver is honest and honestly performing the measurements, we know that if they guess the correct basis, they should definitely get the bit that the sender encoded. So in this case, the receiver is honest, so they did obtain 0. Okay, and so the sender will just check that like this measurement was performed honestly. Okay, and this is kind of the entire this measurement check sub protocol that's happening here. And if like all of these checks pass, the sender can be like reasonably convinced that like the receiver did indeed do their honest measurements. And what third parties do is they basically just get rid of the qubits that were used for this check, and then they use the remaining, in this case 4 qubits, to complete the protocol as before. Okay. So this check in the middle using like a commitments and then like a random subset of openings is meant again to kind of force the receiver to measure their qubits upon reception. And yeah, so this was like Crépeau and Killian's original idea. And again, they didn't actually really have like a security proof of this. So like basically like a lot of work over the next few decades really was about actually taking this main template and saying like, okay, can we construct cryptographic bit commitment protocols that allow us to prove the security of this this OT protocol, right? And so this is kind of the main question that remains, is which cryptographic assumptions suffice to instantiate the bit commitment. Okay. Oh yeah, I think there's a question. If I lie about partition of, let me see. Okay, so there's a question: if I lie about my partition of IB and I1 minus B, what prevents me from learning something about both strings? Okay, good. Right. So exactly. So basically, what's happened here is like if we assume, or if like this commitment check goes well, then basically we're in the situation where the receiver has measured all of these qubits, right? And so they basically lost about half of the information in X. Okay, so assuming that the receiver doesn't know about half the information in X, that means that they basically, okay, so they only really know about half of the string X. So you're right that they could lie about I0 and I1 and basically learn about half of the information of Y0 and about half the information of Y1. Okay, and so you can construct like these encryption, even information theoretic, like kind of encryption protocols or schemes using like hashing, where if you only know like about half of the secret key, you obtain no information about the message. So you really need to know like all the secret key to obtain any information about the message. And that's exactly the type of schemes that are going to be used. Okay.
That makes sense. Thanks.
Okay, cool. Great. So yeah, the question that remains, or that has been like, studied over the last few years is like, well, now that we have this template, what cryptographic assumptions suffice to instantiate the commitment scheme? And so I'll mention a few works and the results they give. So there's a work of DFLSS in 2009 that showed that, okay, if you assume like the specific learning with errors assumption, this is like in this class of like kind of structured assumptions that I was mentioning, if you build the commitments from that assumption, you can obtain security of this oblivious transfer protocol, okay? And in turn, this implies secure computation. So this is nice in that it shows that you can obtain like rigorous security through this template. But there's actually other ways to obtain secure computation from learning with errors, even ways that don't involve quantum communication. So it didn't really give any new like feasibility results. A work around the same time showed that if you build these commitments from any one-way function, you can actually obtain like through this template a notion of weak oblivious transfer, which I'm not really going to explain what that is. The important point for this is that like it's not really the notion of oblivious transfer that we need to get our final implication that we want, which is the task of secure computation. Okay, and then finally, like these two works that I mentioned this past year, finally what we show is that you can build commitments from the existence of any one-way function, plug them into this protocol, and obtain like fully secure oblivious transfer. And like one major difference from like our work in these previous works is that even in building the commitments, we also use quantum communication. Okay, so we use the existence of any one-way function plus quantum communication to build commitments, which then in turn get plugged into this Crépeau and Killian template for OT, and then in turn implies secure computation. So this is kind of the works that finally completed this implication of one-way functions to secure computation. Okay. And so, yeah, I mean, I didn't want to get into
James, sorry to interrupt you. We are close to 12 p.m., so it might make sense to rush through a bit if you can. Okay, there's a question about, do you need two-way quantum communication from Marius?
Oh, yes. Yeah, so I'm actually almost done anyways. I only have like one more slide. And then also to answer that question, yes, we actually do use two-way quantum communication. We use quantum communication from, yeah, exactly, both parties. And I think you can, get away with one-way quantum communication. Yeah, using teleportation, you can get away with only one-way quantum communication as long as you also assume one party can store quantum memory. So you can either use two-way quantum communication or one party with quantum memory. Okay. Okay. And then, yeah, like I said, like I'm basically wrapping up. The takeaway from this talk basically is that quantum communication can be used in place of structured or like strong cryptographic assumptions when building secure computation protocols. So that's the main takeaway. And then one thing you could ask is that like how practical are the resulting protocols? Like do we actually want to use such protocols? Do we want to take advantage of the security trade-off? Do we want to use protocols with quantum communication? And so this is like basically pointing towards like future work. Yeah. So one thing I'm working on right now with Doc Shida and a couple grad students at Illinois, so Amit Agarwal and Nishant Kumar, is we are like studying this question of efficiency through the lens of like, one thing that we can try to optimize is how much interaction these protocols require. Okay, so basically what we observe is like if you're looking at like the Crépeau and Killian template that I just that was up a couple slides ago, there's actually a lot of like really nice features of this protocol. It only requires single qubit states. It doesn't require quantum memory. You can prove it secure against malicious adversaries, but it does require like multiple rounds of interaction. Whereas like oblivious transfer protocols from like stronger like assumptions and using classical communication, in some cases you only need like just 2 rounds, kind of an optimal number of rounds of communication. So this is actually one thing we're trying to study. Can we reduce interaction of these protocols? Maybe even at the cost of like sacrificing some of these benefits of the original template. So we're trying to study some of these trade-offs. And then, you know, there are many other things you could study, like noise tolerance. This is like a big area of study in like quantum key distribution, and I think it probably hasn't been quite studied as much for like these secure computation protocols. Device independence, again, like a major area of research in quantum key distribution, which basically focuses on like, well, let's say that like the devices that the honest parties are using, like the quantum devices they use to prepare and measure qubits, were actually manufactured by an adversarial party. You know, can you still obtain security in the setting? And so this has been studied a lot for quantum key distribution, and it becomes, I mean, it's, as far as I'm aware, it's studied much less frequently and like in secure computation, and it seems like more difficult because of the adversarial model. So these are just a couple other directions, and yeah, I mean, I think this is all I wanted to say. So thank you for listening and for having me, and I'm happy to answer any other questions.
Thanks, James. There was a question by Brian on chat. Let me start with that. Mm-hmm. Is this guaranteeing that I have locked up a single classical bit, or does it also let me commit to a single quantum bit as well? This was in reference to the commitment scheme.
Yeah, the commitment scheme that I was describing was, I mean, that was just about classical bits. You could use it to obtain some notion of commitment for qubits as well. But yeah, the basic protocol that I was describing was just for classical bits.
That's good. Brian and anyone else that wants to ask questions, feel free to unmute yourself and ask at this point, or type on chat and I can convey them.
Oh, can the secure company receiver lie about which function? So the function, right? So the function f is like kind of built into the protocol itself. Like you usually construct a protocol specifically. I mean, you instantiate the protocol with the functionality f. And so like basically the guarantee is that if you're participating in a protocol computing f, the adversary can do anything. They can lie about whatever they want. They can send whatever the messages they want, and they still won't be able to learn anything else about f of x, y. So they can try to like start a protocol about g, but like basically some other f, but basically the other honest party will abort in that case. So yeah.
Okay, thanks.
I have one more question. Marius here. So, I mean, here the main assumption was this existence of this one-way function. Are there other mathematical structures which are equally powerful? Whatever. I mean, you know, the generators of a group or something, some other structure where you have sufficient a sufficient contrast between what you can do and what you cannot do.
Sufficient contrast.
I mean, so the assumption is that you cannot calculate the inverse, right? I mean, are there other mathematical objects where something similar happens? Relations, functions are relations, or you know, some group structure or some number theoretical structure.
Oh, yeah, like different things like hard relations and so on. Like, okay, yeah, I mean, sure. I think the nice thing about like the way that one-way functions, like the way the assumption is usually written, is that it is like kind of, you could write down other assumptions based on relations or groups and some things, but they would probably all just imply the existence of a one-way function.
Oh, okay.
Yeah.
So at the moment, that's just the formulation to do.
Yeah. Mm-hmm. Yeah. It's kind of like the most generic or like the mildest or like weakest assumption that you can kind of reduce everything else to. Yeah.
Okay, let's wait a few more seconds just in case anyone else has questions.
So just another high-level question. So it seems like, I mean, the basic primitive you're using here allows you to verify that someone has sort of measured a whole suite of EPR pairs that are sent. beyond sort of this secure computation, are there other things that you can do using this primitive that are sort of new?
Yeah, actually, there's a lot of things you can. So using, like EPR pairs or BB84 states in this way, I think I mentioned very briefly, like this paper of like Wiesner, like mentioned one thing you can try to do is unclonable currency, like quantum money. So like, states that like can be verified, but like provably can't be cloned under cryptographic assumptions. And this, this is like a big area of research, is like even to this day, is like, can we use like these type of like quantum states to do not only just unclonable currency, but maybe like unclonable functionalities, maybe more specific applications to cryptography, like can we give like encryption schemes with unclonable ciphertexts or like unclonable decryption keys and so on. And all these things, of course, cannot be obtained with just classical information. So these are types of things that are that quantum information is specifically used for.
Great, thanks.
Okay, so thanks again, James. And thank you everyone for coming.